Welcome. So, we will discuss today the 8th week assignment, and that is mainly on higher layer issues and the navigation satellite system. So, let us start on the assignment and answers. The first one, this short forms I hope you remember, retransmission timer timeout, that is if RTO fires after CWND reached 64 kilobytes, how long it will take to reach throughput of 128 kilobytes per second. Seems to be a little bit trick is there, throughput has to be calculated, and what is given is assume RTT is 0.5 second, segment size is also, but a similar number, but unit is different, segment size is 0.5 kilobytes, and 4 options are given: 32 second, 35 second, 3 second, 5 second. So, let us try to understand what really happens if there is a RTO firing when CWND value is given, it has reached some value. After a RTO fires, there will be change in CWND and SS threshold, and depending on their values we have to decide whether it is a slow start or congestion avoidance phase. And then it says that from there it will start, and when it will reach the throughput of 128 kilobytes. So, for 128 kilobytes per second, what should be the CWND that should be at the end, that let us try to find out. So, at CWND 64 kilobytes and RTT equal to 0.5 second, throughput is CWND by RTT, which comes out to be 128 kilobytes per second. So, that means 128 kilobytes per second throughput means CWND is 64 kilobyte. The question is intentionally given like that, you come back to 64 kilobyte. So, if you read the question now, it says when CWND has reached 64 kilobyte, there is a RTO firing. So, some changes will happen when you come back to 64 kilobyte again, when again CWND becomes 64 kilobyte, that is the question, that total time duration. So, let us see. After RTO fires, the SS threshold will be reduced to that time whatever CWND divided by 2, and CWND will be reduced to 1 segment. So, new SS threshold CWND was 64 kilobytes divided by 2, that is 32 kilobytes, and CWND will be set to 1 segment 1. Now, CWND is less than SS threshold. So, therefore, it is a slow start. So, in the slow start phase, the duration is the RTT into log 2 of 32 by 0.5, which comes out to be 3 seconds. This is number of RTTs, this is each RTT. So, it comes out to be 3 seconds. Now, after 3 seconds, it is entering congestion avoidance phase, because CWND is now equal to new SS threshold. So, number of RTT in this phase to reach the CWND to 64 kilobyte, that is the target, from now it is 32 kilobyte, and in increment of 0.5 kilobyte each is difference of these two divided by 0.5, because it is linear increase, that comes out to be 64. So, 64 RTTs will be required, and each RTT is 0.5 seconds. So, it comes out to be 32 seconds. So, congestion avoidance phase it is 32 seconds, and slow start phase it is 3 seconds. So, total duration is 35 seconds. So, therefore, the appropriate choice is B. Now, let us see second one. Find the duration of slow start without loss of any segment. The parameters specified are RTT 0.5 second, SS threshold 64 kilobyte, and segment size is 0.5 kb. It is a part almost similar type of question. Options given are 2.5 millisecond, 3.5 second, 2 second, 3 millisecond. Okay. So, let us see. Number of RTT in slow start phase is log 2 SS threshold by segment size, and duration of slow start phase is RTT multiplied by number of RTT, which comes out to be 3.5 second. So, the option is B. This was very simple. Let us see next. In a satellite based data communication system using TCP, the header is used in TCP segment only, IP segment only, satellite MAC frame only, or all of this where the header is used. Let us try to recollect our original picture. The application data is sent to the TCP and TCP is segmenting. In TCP segment, from the application data it adds a header. It takes out this segment which is maximum segment size of the application data and adds a TCP header which is 20 bytes. Then it passes on to the IP layer, and IP takes, including TCP segment header, it takes the whole, treats the whole thing as a data for IP data, and it adds its IP datagram, adds its own header. That it passes on to the MAC layer, and that also treats the including IP header whole thing as data, and it adds a header as well as sometimes a trailer. So, it seems that each of these layer add their own header. So, therefore, each segment uses their own header. Correct option is D. Next, which of the following are the characteristics of the transmission control protocol TCP? Which of the following are the characteristics? Is or are, it can be one or more. Maintaining the source and delivery port address, reliability, flow control, all of these. So, let us see the TCP or transmission control protocol does what. The transmission control protocol is connection oriented. So, therefore, who is connected to whom is to be known. So, source as well as destination port address is maintained. So, first point is covered. It protects both header as well as data, thereby making it reliable. So, that is also agreed. It has the capability of controlling the flow of the packets depending on the network load and receiver capacity. So, it does the flow control also. So, all of these it does. So, therefore, all of the given choices are correct, which is the appropriate choice is D. Okay. Next one. For fixed window size, if the round trip time increases due to a satellite channel, the throughput will increase, decrease, remain unaltered, or throughput does not depend on RTT. Let us see. The round trip travel time is twice the satellite channel 1 hop transpropagation delay. 1 hop it goes from sender to receiver, and from there it comes back. So, it is a round trip time. Throughput of the channel can be calculated by taking ratio of the window size to the round trip time. That is the throughput calculation. We have done this calculation earlier. Therefore, for fixed window size, if the window size is fixed, then and if RTT changes, throughput will always decrease by increasing RTT. In satellite case, RTT is increasing compared to the terrestrial. So, therefore, throughput will decrease. So, the appropriate choice is B. Next, our TCP connection is set with window size of 64 kilobytes, uses a satellite with 1 hop delay of 300 millisecond between sender and receiver stations. The maximum possible throughput is, some numbers are given in megabits, 8.066 megabits, 0.08533 megabits, 8.066 kilobits per second, 0.8533 kilobits per second, all are throughput because bits per second is given. Now, this seems to be the similar type of problem. The throughput of a link can be determined by using the formula throughput is window size by RTT. Just now we have talked about it. So, RTT is the delay for the signal to travel from sender to receiver and back. In this case, it is 2 into 1 half delay. So, throughput is, it is given in bits per second. So, we convert byte into bit, 64 kilobyte into 8. So, that many bits divided by 2 times 300 millisecond, which comes out to be 0.8533 megabits per second. The correct option is B. This is a GNSS. In GNSS signal model given below, which parameter contains the satellite ephemeris? The signal model is given as YIT, I stands for the satellite number, is equal to root 2 CI into dit into CIT cos of 2 pi FIT plus phi I. Now, in this, whether the satellite ephemeris are in C, capital C, or small d or small c, or in F or in phi, the choices are given. A, B, C, D, different choices are given, phi, capital C, small c, d. So, let us try to understand what is this. The GNSS signal consists of carrier power, navigation data, PRN codes, carrier frequency and carrier phase. And GSS signal model is expressed as the same expression is written here, YIT is equal to root 2 CI DIT CIT cos 2 pi FIT plus phi I. Now, in this the carrier power is represented by the capital C and navigation data is represented in small d. The PRN code is represented in small c. The carrier frequency is F and phase is phi. And in all these things the ephemeris is available in the navigation data, that is the ephemeris sent by the satellite. So, navigation data contains the satellite ephemeris. So, therefore, the small d will be the answer. So, correct option is D. At D we have said it should be small d. Okay, next. Again on higher layer, if SS threshold is 128 kilobytes and segment size is 500 bytes, find how many RTT will be required for CWND equal to SS threshold during slow start phase. Options are 32, 16, 4 or 8. This is when it starts, when CWND is much lower than SS threshold, it starts and goes up exponentially, and when it reaches SS threshold it goes up linearly, slow start phase and congestion avoidance phase. This x axis is time in number of RTTs, y axis is CWND value. Now, SS slow start phase is when CWND is less than equal to SS threshold, this lower part, the green part, and during the slow start CWND increases by 2 to the power n exponential, and n is the number of grouped transmission. Time to reach the SS threshold is small n into RTT, these are in terms of RTT. So, this will be the time. So, we put the values as CWD increases log normally in slow start phase, 2 to the power n is SS threshold by segment size, SS threshold value is given, segment size value is given. So, 256 is the number, n is equal to 8. The total number of RTT is 8, appropriate choice is D. An observer, this seems to be an elaborate question, an observer at the geographical north pole, XYZ coordinates are given 0, 0, 6, 3, 7, 8, has a GPS receiver which at an instant of time measures same delay from all 4 GPS satellite and delay value is given in second. The 4 satellite coordinates at that instant is available for their XYZ coordinate, 4 of them are given, and where all distances are in kilometer, large numbers. Determine the clock offset error in GPS receiver when the velocity of light is given, which is not exactly 3 into 10 to the power 5 kilometers per second, it is 2.99792458. So, the GPS receiver will have some clock offset and the time delay measure is given, velocity of light is given. So, a pseudo range can be calculated, and it says that range for all the satellites whose coordinates are known are same. So, with these information and the user coordinate information, we have to find out what is the clock offset. Let us see how do we proceed. Though numbers are large, but it may become easier. The measured time delay is given, t is equal to 0.17097528 second, velocity of light is given 2.99 etc. So, pseudo range is multiplication of these two, which comes out to be 51,257.09945 kilometer. Pseudo range is known. Now, we know for 4 satellites j equal to 1 to 4, rho j, that is the pseudo range for each satellite, is a square root of x j minus x u whole square plus y j minus y u whole square plus z j minus z u whole square plus c into t u, that is clock offset, c is the velocity of light. Now, interchange the side. So, rho j minus c into t u and squaring that, so that right hand side the square root can go out, it becomes x j minus x u whole square plus y j minus y u whole square plus z j minus z u whole square. Now, here x j, since all the values the pseudo range values are same for all satellites. So, you can take any one of the value of x, y and z, one of the satellite, and x u, y u, z u are given, and rho j value is found out. So, you can find out c t u. If we put the number, since all ranges are same, we can take any one of the satellite coordinate, also user coordinates are given. So, putting these values, there are a lot of zeros since it is at north pole. So, you will find out that T u comes out to be 0.1 second by just putting these numbers, which is our option A. So, though numbers look very large, actually the calculation method is very simple. Now, let us go to the last question, that is measured received signal from each GPS satellite contains signal power, PRN code identifying the satellite, navigation data, measured code delay, transmission frequency with Doppler offset. This we have seen earlier in one of the questions. For initial signal acquisition, which two parameters are searched? There are many parameters are given. For initial signal acquisition, navigation data and PRN code are searched, or PRN code and code delay are searched, code delay and frequency are searched, or none of these. Let us see. So, this expression after the delay, this is at the receiver, the expression becomes in terms of tau, that is the delay, code delay, it comes out to be yit is, this is summation of all the satellite signals. So, they will come together, which is root 2 c I d I t minus tau c I t minus tau cos 2 pi f f r f plus f d I, this is the Doppler f d I and t. So, tau is the code delay, because the path delay is there and code is shifted. So, we find out in terms of code, it is code delay, which is variable, and d f d is the Doppler. So, delay in code arrival and Doppler frequency, these two are variable pair, and then search is done in frequency and code delay. In these different bins, you search where the signal is falling. So, in the search space, say signal is actually in this bin, you go on searching in delay as well as in terms of frequency. That is the mechanism of search in the receiver. But our question is which pair? So, this pair was delay in code and Doppler frequency. The correct option is C. Right. So, thank you very much. With this, we close the assignment 8. Thank you.